Okay, so in this video we're going to kind of revisit a little bit of Unit 2 topics, okay, that being acceleration and how that is related to force. That'll be the next video. Okay, but let's first talk about centripetal acceleration. Okay, so recall from kinematics that acceleration, all right, is the rate of change of an object's velocity. So what's really going to change about that object? Well, the magnitude of the velocity can change. Right, we speed it up, we slow it down. The direction of the velocity could change, right? Or you can change both, okay? And so the way you think about this is that the magnitude changing is our straight line, right? So our unit 1 and 2 stuff, okay? Direction change is actually what we're focusing on now, okay? So unit 5. When we change both, right, then we're really going to kind of move into the world of a calculus-based physics class, okay? Because when you change the acceleration and the direction, you have to do some fun things in terms of calculus, okay? But again, this is just an algebra-based course, so we're not really going to visit that part of physics, okay? So what we're really going to study here in rotation is something called uniform circular motion, okay, or abbreviated UCM. So what happens in UCM is that the direction of velocity is going to constantly change, right, even though the magnitude will remain the same. So let's say I have an object traveling in a circle, right? So here's my object, okay? What happens is everywhere along this path, right, and for some reason it did its own little arrow there. Okay, so everywhere along this object's path, it's going to have this velocity that actually ends up being perpendicular to the motion, right? But the magnitude of that velocity will not change, okay? So how do we produce this constant velocity but essentially constantly changing direction? Okay, so with the direction of velocity changing, it means that there is an acceleration associated here. Okay, so we're going to have an acceleration with this uniform circular motion, and this is kind of relevant to whenever you drive a car. You're going to see that the car will be accelerated when you take turns. So the sharper the curve and the greater the speed, the more noticeable this is. And you'll see when we look at the equation what is meant by this. Right? So the acceleration of an object moving in uniform circular motion resulting from some sort of net external force is what we call centripetal acceleration. Okay, and so this is the acceleration that is producing this circular motion. On my diagram, okay, the word centripetal literally means center seeking. So there's this center seeking or a perpendicular acceleration to the velocity that is constantly changing the direction of the object in circular motion, right? And so the word centripetal literally means center seeking. Now, I did not use the F word, and we'll get into that here in a little bit, okay? That word does not exist in physics, okay? And that's because it comes from the idea that if you want to cause objects to spin, you generally put it into what's called a centrifuge, but don't put the letters AL at the end, right? Drop the E and put the AL, okay? We don't use that word here, all right? So therefore, the direction of the acceleration is always pointing into the center of the circle. And this is going to actually end up being our positive direction in circular motion, all right? So the formula is simply A sub C equals V squared over R. And so the C signifies the centripetal acceleration, right? And so we're going to take the linear speed, square it, and divide it by the radius. So what you can see from the formula is greater the velocity, right, or greater velocities and smaller radii is going to produce greater accelerations, okay? And so if we want to talk about in terms of what are our relationships, A sub c is inversely to 1 over r. It's also directly proportional to v squared. Okay, so basically if one goes up, so if I increase my radius, that means my acceleration will go down. If I decrease my radius, my acceleration will go up, right? So they're opposite each other. And then when you do the velocities, they're directly related. So if one goes up, the other goes up. Or if one goes down, the other goes down. Now, there is a second version to this, and this brings in the rotational, or the angular velocity. So if I just simply substitute that in to my v, my equation, so v squared over r, sorry, there was something on my screen. So what I'm going to do is I'm going to put r omega, right? So r omega squared over r. And now I square the top, so I get r squared over omega squared. And now this radius, right, it's the same circle, so the radius in the denominator cancels one of the radii up top. And so my equation then becomes, and this is, again, this is a second version of the equation, omega squared r. Okay. Now, again, this is if they give you angular velocity. If they just give you the linear velocity, just plug in that v. Okay, you don't have to do anything with omega for those questions. So this first example says, what is the magnitude of the centripetal acceleration of a car following a curve or radius 500 meters at a speed of 25 meters per second, which is about 90 kilometers per hour, which actually works out to be about a highway speed. All right, and then compare this acceleration with that due to gravity for this fairly gentle curve taken at a highway speed. Okay, and so what we're going to do, we're just going to find the centripetal acceleration. And this question is very typical. They always want you maybe report it in terms of g. All right, and so we're going to plug in our velocity, which is 25 meters per second, and we're going to divide it by our radius. So we're going to do 25 squared over 500, and you get a centripetal acceleration of 1.25 meters per second squared. All right, so you can see very easily we plug in numbers, we multiply, we divide. Okay, now the second half of the question talks about what is essentially the ratio of centripetal acceleration to g. And so what happens is when we talk about g force or g value, g force is really an acceleration. Okay, and we're comparing that acceleration to the amount of g's. So we're going to set the ratio of a sub c to g. And so for this one, we're going to divide 1.25, which is the acceleration in centripetal motion, divided by 9.81. You can use 10 if you would like, and just move it 1 to the left, and you find that it's going to be 0.127 g's. Okay, so that means it's just greater than a tenth of what we feel just standing on Earth, right? So sometimes when you do these questions, this is something like, why do I feel heavier when I go over a turn or around a curve? Why do I feel lighter? Okay, so you can simply see why by just looking at, in this case, right, we are going much less than what g is. Okay. The next question says, calculate the centripetal acceleration of a point 7.50 centimeters from the axis of an ultracentrifuge spinning at 7.5 times 10 to the fourth revolutions per minute, and determine the ratio of the acceleration to that due to gravity. Again, there's that very classic second question talking about compare it to g. So the first thing we actually need to do is take this revolutions per minute and turn it into radians per second. Okay, and to do that, we're going to do our conversion factor. 1 revolution is 2 pi radians, and there are, in 1 minute, right, there's 60 seconds. So we're going to do this should be 7.5 times 10 to the fourth, sorry. So we're going to do 7.5 times 10 to the fourth times 2 pi. Now my calculator is going to give me the number in terms of pi, and I'll just hit a special button, and it'll give me the right answer that I'm looking for. So it's going to be at about 7,900 radians per second. Okay, so now we have our angular velocity. That's what this is equal to. And so what we're going to do is we're not going to use the v squared over r version of the formula. We're going to use the omega squared r version of the formula. And the only other thing that we need to do here, right, is we need to convert this 7.50 centimeters right, to 0.075 meters. I don't know what's going on. Must be something trapped in my screen. Okay, and so when we do that, we're going to do omega squared, so 7,900 times, I forgot to square that, 0.075. So 7,900 squared times 0.075, and we get an answer of 4.68 times 10 to the 1, 2, 3, 4, 5, 6 meters per second squared. Okay, and now we do the same ratio of that number, so 4. I always decide to pick the pencil when I want to use blue because I see blue, right? So we do 4.68 times 10 to the 6th divided by 9.81, and we're going to get this many g's. So we're going to do 4.6 exponent 8. Again, if you have a TI calculator, use that EE button. Okay, and we're going to get 4.77 times 10 to the 1, 2, 3, 4, 5, 6. Oh, how did it grow up? Oh, I put in the wrong value. It didn't grow up, it got larger because I put in exponent 8 instead of exponent 6. And so it should just chop off 2 decimal places. So 1, 2, 3, 4, 5. Okay, so 4.77 times 10 to the 5th G's would be that comparison, okay, to our G value. Okay, so this is our G force. All right, so in the next one we're going to actually dive into, right, if we have an acceleration, well, we have an associated force, and that force is called centripetal force. And then we'll do Newton's law of universal gravitation.